Okay, I'm waiting.
I'm waiting. Yeah. So hello, good morning, everyone. And today we are meeting for our second set of presentations by the participants for Astronomy from Archival Data. And like yesterday, everybody gets 10 minutes each. At 8, we'll give you a reminder. But obviously, it's more or less democratic. So if you need to exceed it also for some reason, that's fine. So today we have 12 presentations, and we'll start off with Raisa because it's midnight for her. So she can talk to us and then have a good night's sleep. Sorry, Raisa. Continue. You can start.
Oh, okay. I was afraid the connection
No.
was not working.
That window was open.
So, hello everyone. My name is Raisa. I'm from Brazil, so that's why it's the middle of the night for me. And today I'm going to present what I have done in the Galaxy Morphology project. I started this project 2 weeks ago, so I didn't got around to do much, but here's what I did. So the goal of this project is to study the morphology of galaxies. And to do that, we use a program called GALFIT. This program can fit the light of astronomical objects, not only galaxies, it can fit the profile of globular clusters, protoplanetary disks, and a lot of other things. And I use this to fit the light of galaxies. And as I am a beginner, I have only used a very simple model that assumes a bulge for that assumes a Cersei profile for the bulge and an exponential profile for the disk. My idea here was to do this for a few galaxies and see what kind of substructures were revealed when you subtract the a bulge and a disk contribution. So I used the Cersei profile for the bulge. It's very pointy in the middle, it's very concentrated. There are 7 free parameters: the half-light radius, total magnitude, and the coordinates of the center of the galaxy, and the ratio between the minor and major axes, and also the position angle of the galaxy in the sky. This is going to be a bit clearer when I talk about how I obtained these parameters. And for the disk, I used an exponential profile that is actually a special case of the Cersei profile when n is equal to 1. And it has the similar free parameters. The only change is we don't use the half-light radius here. We use a scale length, but it has a relation with the half-light radius. And to actually run GALFIT, I had to get these parameters from somewhere. And to do that, I used the source extractor, which is a program that creates a catalog from an image. It tells you what objects are stars, what objects are galaxies. And for galaxies, it tells you also the the length of the major and the minor axis, the the position angle of the galaxy, it's this theta. The elongation is the ratio between the major and minor axis. And it also performs a little bit of photometry, so it gives you an estimate of the magnitude of the galaxy. I used specifically the Mag Auto, And it also gives you an estimate of the sky. It's the background. I ran Source Extractor in local mode, so it estimates the sky very close to the galaxy. I thought this was a better estimate. And I also used IREF to manipulate the images, crop them, edit the headers, and to calculate the residuals that I'm going to show you. So for the galaxies, I used these three galaxies from the Coma cluster, and I chose galaxies that were solitary, you can say. They weren't so close to other galaxies. They weren't cropped out of the image, so I chose these three because I thought they looked like they could be elliptical galaxies, and the simple model that I'm using fits well for elliptical galaxies. So for the first galaxy, I used the Cersei profile with a concentration parameter equals to 4, and the disk and the residuals from this model showed me that this galaxy is not an elliptical. It's actually probably has spiral arms and a bulge, probably a bar or something more complex. And after this, I tried to fit a simpler looking galaxy, this one, which is very round. I thought this probably could be an elliptical. And I fit only a Cersei profile at first because the Galfit manual says that ideally you should build the complexity of the model you are trying to fit. So when I fit the Cersei profile, the residuals didn't look so good, and I went back and added extended disk for like this emission, and I could see that the light of the galaxy was almost completely wiped out from the image. So this model was a good fit. This galaxy didn't show any underlying substructures. And then I went for the third, the elliptical looking galaxy. And when I subtracted the model, I saw uh, this structure here, which I think might be spiral arms and probably a bar here. And after I fit all these galaxies, I also tried my hand at fitting multiple galaxies at once. So I picked this crowded region from one of the fields, and I tried to fit multiple models at once, but always keeping this bulge and disk idea. And when I subtracted the models, I could see that like this galaxy here had left a very small residual, but very round. But the other ones, and the central one especially, didn't. The central one actually is probably an irregular galaxy. It has this extended emission here. The residuals don't look so symmetric. And these other smaller galaxies, the residuals came out very interesting because when you look at this, you can see that these things are probably on spiral arms or an irregular morphology in this case. This led me to conclude that this galaxy here is probably interacting with these other galaxies. It's a harassment, and that this is basically what I did until now. My next steps are going to be get better at estimating the half-life radius. As of now, I have tried, it was basically trial and error. I'm trying to find out how I can use an isophoto analysis to figure out the half-life radius. And I'm also going to read the very lengthy section of the manual that talks about how to fit bars and spiral arms to see if I can fit those two galaxies that I showed you that had a substructure. And that's all.
Thank you. That was an excellent presentation, a very good one.
Thank you.
Very good. And and
yeah, very well presented, Aisha. Yeah,
one more.
it's okay. Yeah, well presented, Raisa, and let's hope we can continue with your work on. Yeah, there's a lot of potential in what you are doing. You've done very well, and yeah, I congratulate you. And keep in touch with
Yes,
the. And let's
I'm
continue.
very excited to continue the project.
So, like we mentioned, we're going to have another project which we'll be sending you all the links and all very soon, which is called Astrosprint. And that's when we'll take off from this level, which since now all of you all have GalFit running, IRAF running, so we can do isophotal analysis as well as some more features, right, which we didn't get time to do this time. So we will continue, and that was a good presentation. Thank you. Do any of the participants have any questions? Please ask questions if you have any.
This is Tim Hamilton here. I've got a question on you. I was impressed with how clearly some of the bar and spiral arm structures would come out when you were subtracting your simplest model. When you were able to add in the other features, the more complicated model, how low did the reduced the chi-squared per nu, come out? Do you remember what the lowest value was?
Hi, so did you hear the question?
Yes, but actually I didn't get to this very quantitative analysis because I was actually, I don't know, I got fit running in a week or something, and I tried to, as I said, there was a lot of trial and error involved. So what I did basically was to fix the scales, the color scales in both images, the original image and the subtracted image, and I kept changing the parameters and seeing if the residuals got better. But now, as you were saying, the next level of the project would be to get into these little details of how good is actually this fit, or how can you make the estimates better. So sorry, I don't have actually an answer for you because
That's okay.
I didn't
That's
get
okay.
there yet.
Yeah.
I was just curious because it looked like a very good fit, in fact, the first one that you'd shown there. And I'm
Mhm.
using the same software for some of my research right now. And one piece of advice, which it seems like you're following right now, is don't try to fit too many things to it. Start with, as you're
Mhm.
doing, start with a simple and work your way up and gradually add in features. But you can get to a point if you have too many parameters that the model can get stuck in what's called a local minimum, local chi-squared minimum, where it thinks it's a good model, it can't find a better one, but it's actually something that's not very physical. And so you just have to gradually add those parameters in until it looks about as good as you can make it, and don't try pushing it too far past it. But those
Mhm.
look very good, what you had.
Yeah, thank you.
Yeah.
As a beginner, I'm very happy.
Yeah. So Tim, actually, in defense of the students, what happened is a lot of their time just went in installing the software, right? I mean, you know how it is. When
I
you
know how it is. I
install
made the mistake
IRAF
of trying to
and
teach some of
GalFit
mine
and
IRAF one semester, and I spent about half the semester trying to get them to install it.
yeah. So
And Galfit has a decent learning curve there.
Yeah.
And they got all-
Yeah, they need IRF for the residual image and to do some stuff on it. So it was I think a lot of installation exercise. But hopefully now when we go on to Astrosprint, the one which is next month, then by then they can take off from a running Galfit and a running IRF. Then probably it will be better. Yeah. So but Raisa, yes. So Tim's comments are very valid. That basically you have to assess later on, right? The goodness of the fit and your residuals. What's left? The stats about the residual image. Right. Okay. So thanks, Raisa. And you can have a look at the other presentations and the recordings, right? They'll be there on YouTube anyway. So let's continue. And our next presentation is by Sargam. Yeah.
Hello, hello. Is my voice is coming?
Yeah, we can hear your voice. Now you just share your screen.
Ma'am, I have been my audio. There is a issue with my audio with computer, so I will be projecting my screen through my computer, and I will be talking from my phone.
Very good. We do that often. Sometimes there is a problem. We are forced to do that. So it's okay. We can hear both. No problem.
Okay.
We do that quite often. Once in a while.
The screen is visible.
Only put it on screen share, slideshow. Yeah, very good. It's perfect now.
Before proceeding, I will be remember for the today. Today is our National Science Day, remembering the discovery of Raman effect. So we are celebrating the National Science Day today. So coming to my project is the exoplanet. My name is Sargam Barekar, and it is supervised by the Professor Tim Hamilton. Uh, Introduction. The exoplanet. The exoplanets are any planetary body that is outside the solar system and usually orbit star other than the sun. The first exoplanet was discovered in 1917, but it was officially confirmed detection in 1992. As of now, astronomers have confirmed more than 4,000 exoplanets revolving around the distant stars. For the project, we have taken account for the 5 exoplanets mentioned in Exoplanet chapter, the book by the Tim Hamilton sir, which are the Kepler 4b, Kepler 5b, Kepler 6b, Kepler 7b, and Kepler 8b. The Topcat software was used to calculate and measure the data from the archival data. The first planet was Kepler 5b. There are the 5 planets, so I will be does not talk much in detail for the 2 or 3. I will be talking for the details in Kepler 4b. So the Kepler 5b. The period of the Kepler 5b is around 3.548 days. Orbital radius was 1630 meter, which is 1.08 astronomical units. The planet radius was found 1.05 into 10 to the power 8 meters, which is similar to 1.52 in terms of radius of Jupiter. Mass of the planet was found 6.19 into 10 to the power 26 kg, which is around 0.32 times mass of Jupiter. The temperature of this planet measured by a rocket 5132 degrees Celsius, and density was measured 125.48 kilogram per meter cube. As of you see the as you see the veil around the normalized flux and the phase index, you can see uh, there is a there is a mm, there is a well established curve uh, around the around the dots around the dots. So we go to the next thing, the Kepler 6b. The Kepler 6b is a planet with period around 3.2346 days. Its orbital radius is 6820101145 meters, which is around 0.046 astronomical unit. Planet radius was 9.87 into 10 power 7 meters, which is around 1.43 radius of Jupiter in terms of radius of Jupiter. Mass of planet is 1.19 into 10 power 27 kg, which is around 0.63 times mass of Jupiter. The temperature of this planet is 1816 degrees Celsius, and density 28 289.59 kilogram per meter cube. Kepler 7b. The period of this exoplanet was 4.885 days. Orbital radius is 93348 85 triple one meters, which is around 0.062 astronomical unit. Planet radius is 1.18 into 10 power 8 meters, which is around 1.70 radius of Jupiter. Mass of planet is 1.47 into 10 power 27 kg, which is around 0.77 times mass of Jupiter. The temperature of this exoplanet is 1959 degrees Celsius, and the density is 213.69 kilogram per meter cube. I have been focusing on the exoplanet mentioned by the Tim Hamilton sir is the Kepler 4b. It has a different it has a different curve um, than the most of the other exoplanets. It has a weird kind of um, um, weird kind of curve, which is uh, because of its the radius around its star and the mass of the planet, and it is small in comparison with the other uh, four three planets. So the period of the Kepler 4b is 3.2143 days. The orbital radius was found 68088547776 meter, which is around 0.045 astronomical unit. Planet radius was 2.74 into 10 to power 7 meters, which is around 0.39 times radius of Jupiter. F trans is found at 0.9993. Delta F was found 0.0007. The mass of planet is 1.19 into 10 to power 27 kg, which is around 0.62 times mass of Jupiter. The temperature is found 1971 degrees Celsius, and the density is 13852.04 kilogram per meter cube. Uh, the radial velocities of the Kepler 4b is is different than the most of the other planets, and it is a very it is the planet is very close to its star, so that it revolves um, mm, when it is take to the close to the star, it revolves very fast around the star, and goes like uh, after the after this wing. For this project, I have taken account this reference, uh, mm, the mass archival data, and mm, the exoplanet chapter was provided by Team Hamilton sir, and the exoplanet .eu catalog. Thank you.
Thanks, Sargam. So, Tim, you can ask your questions, or the others can. Yeah, Tim, you can give your feedback, and the others can ask their questions.
Yes, Sargam. So it looked like you'd been able to get out the data, even in some of those very difficult cases, like the one that had the very low, the high noise levels there. Um, I don't have much to say about it, except that it looked like you had been able to get that work done. So good job.
Yes, sir. I have uh, taken that account. For you have mentioned that some of us taken should be taken the Kepler 4b. So I have worked on that, and I have found that the similar result.
Yeah, great. So actually, they did the list that was mentioned in your chapter, right? The list, the same objects which you had mentioned.
Yes, yes.
Yeah, so I made all of them do the same thing so that they can compare their results and see what it is like. Next speaker. Yeah. Okay. So thanks a lot, Sargam. Do any of the participants have any questions? Does anybody want to ask? Please, we would like all of you to be interactive. Please talk to the others, right? This is a very good platform in which you're getting to meet other people who are interested in things you are interested in. And otherwise, the chances of you all meeting would have been quite bleak. So please interact with each other. And I would be really happy if you all ask each other questions, right? Even if you think it is basic, but it's good to have your basics fixed, right? So does anybody want to ask anything? Please ask, right?
Excuse me,
Ma'am,
ma'am. I was asking one thing.
Yeah, please do.
Ma'am, may I continue?
Yeah, please.
Yeah, ma'am. I was asking one thing, that how did he calculate the albedo value for the temperature thing for the exoplanets, especially for the Kepler 4b planet?
It is assumed as a team sir mentioned in his exoplanet chapter. The albedo value is 0.07, which is assumed. So and it is taken account for the all other exoplanets also during the measuring the data.
And I'll note that although I don't have it in the book, there are ways that it can be calculated that would be beyond what we could do here. One technique that could be done is when the planet swings around not in front of the star, but behind the star, just before it disappears behind it, it would be reflecting extra light back to us. So the total brightness that we see would go up just a little bit. By looking at the transit, you know how large the planet is. By looking at it going behind the star or just before it goes behind the star and seeing the extra light, it would be possible, if that can be detected, to calculate the albedo. But we don't really have the resolution to be able to pull that up here.
Okay. So does that answer your question, Priya?
Yes, ma'am. Thank you, sir.
Yeah. And what about the others? Please interact. Yeah. Okay. So thanks, Sargam. We'll move to the next speaker, Tejinder.
Thank you, ma'am.
Are you there, Tejinder? Tejinder. Is Tejinder there or not there? Then we move to Karthik. If Tejinder comes later, we'll add him. Otherwise, Karthik. Karthik, are you there? Is Karthik there? M. Karthik. What about Akhan Hanif? Akhan Hanif, are you there? Okay, Sukhwinder. Sukhwinder, I think you're there. Yeah. Sukhwinder, come, you can start.
Yes, ma'am.
In cases the people have been missed because they didn't join in time or whatever, please leave me a message on the chat window, so I'll remember to fix you right here.
Ma'am, will I start my presentation?
Yeah, please. Share your screen and start.
Yeah, I'm starting to share my screen. Yeah.
Those people are not coming. Sukhwinder, it's not yet come up.
Yeah, I'm just trying, ma'am.
No problem.
Yeah.
Yeah, great. Only you need to get to the first slide.
Yeah, ma'am. Somehow not working. Just give me some time, ma'am.
No problem, don't worry.
Yeah. No, I'm not yet.
Yeah, it's perfect. It's all good. You can start.
Yeah, ma'am. I have to go to the starting slide.
Okay.
Yeah. Yeah, good morning, everyone. I really feel privileged to put my presentation today on National Science Day. And all thanks to Priya ma'am and Nazam sir for a wonderful initiative, Astronomy from Archival Data. And I would like to, it is really a great learning experience, and we're looking forward to the next project that you are starting. And before I begin, I would like to thank Professor Tim Hamilton, who is the supervisor in this project. His valuable inputs and guidance for the project really helped me to go through it and put up this presentation today. So now I will like to go through the highlights. So I will start with brief description of the concepts involved in this project, and then discuss briefly about the data selection processes used, and then go ahead with the methods applied, and then discuss the results. Now what is this concept of gravitational lensing? Now, the deflection of light by the starlight was predicted by Einstein in his theory of general relativity, but he himself was skeptical about the observability of this lensing phenomena. No doubt, in 1990, the solar eclipse, the solar eclipse did marginally reflect the starlight due to sun's gravitational field. However, for an optical arrangement of a lens whose mass density is in the projection is above critical value, can multiply and can produce multiple images and magnify the background source. This is called strong lensing. There may be weak lensing and micro lensing as well. Now, this gravitational lensing phenomena, is it similar to somehow the conventional optics? No. As in conventional optics, in case of gravitational lensing, there is no single focal point. That is the basic point of difference here. But there are infinite lines of magnification, theoretical magnification lines called critical lines. When they are transferred to source plane, they become caustics. The location of these lines depend upon the relative distances between the lens and the source, and of course on the distribution of the matter in the lens. An infinite number of these critical lines appear to form a ring around the lensing galaxy. It may appear in the form of cross, that is named as Einstein cross, and the ring we called Einstein ring. Now, the first spectroscopically verified gravitational lens was found way back in 1979. It's SPS 0957 561. Here A and B represent the two images of the distant source quasar that were visible, that were lensed by the intervening galaxy or intervening lens that was at a redshift of about 0.355, whereas the quasar was at a distance of at a redshift of about 0.413. Now, this is the schematic of strong lensing, gravitational lensing, and image courtesy go to Tim Hamilton. It was present in his matter that he has given to us. So here we see the light paths from the source to the past the lens and to the observer on the Earth. The galaxy in the cluster act as a lens, and the blue dot that you see is the distance source, and the two white dots are the images that are visible to the observer due to the lens. Now, the second aspect that is related to this project is dark matter. Now, what is dark matter? It is really a big mystery as yet. We don't know what is it. The concept of dark matter as a significant component of the universe was way back in 1970, following the realization that most galaxies are surrounded by unseen halos. The null result of the galactic micro lensing surveys, as well as the abundance of light element produced in Big Bang, suggests dark matter is non-baryonic. But both strong and weak lensing have barely indicate considerably added to our knowledge of distribution and amount of dark matter. In currently favored cosmological scenario, the matter content of the universe is dominated by cold dark matter. In cold dark matter scenario, the galaxies form within the potential well of the extended dark matter halos. Now, the first technical breakthrough in the gravitational lensing arose from improved sensitivity to faint lensed feature, efficient and large telescopes. The second technical step forward arose from the improved angular resolution. The Hubble Space Telescope's images resolve these lenses in the SLAC survey. Now, the criteria for the data selection, as the project suggests, this is astronomy for archival data. So, for high surface brightness compact elliptical galaxy as lenses, we have selected 13 spectroscopically verified strong lenses of known redshift for both lens as well as the source galaxies from the archive masked HST. Now, these 13 these 13 lens selected, the FITS file for these 13 lenses were uploaded, and it was make sure that the filter used is f814W, and on the camera ACS WFP2 on HST. So these are the selection criteria for the data to be used in the project. Now all we need to do is to find the dark matter. We actually need to find the total matter first within the ring, within the Einstein radius around the lens. So now I will go through the various steps involved in calculating this total mass, because it may appear that a single formula will find the total mass, but there are so many intricate steps involved in it. So as you can see, the following formula for total mass in convenient 10 to power 12 solar masses units, we see some D's. These D's are the angular diameter distances. Like as in the figure, image 1, you can see DSO is the distance between source, that is the source which is being lensed, and the observer. And DSL is the distance between source as well as the lens, and DLO distance between lens and the observer. But where do we get this? We have to, and one more point, the DSO, as the figure may led you to believe that but DSO is not equal to DS plus LO owing to the redshifts involved. Now, here we have calculated these D's, the angular diameter distances, using net-right calculator, online calculator, assuming the following omega matter to be 0.286 and omega vacuum 0.714, and H0 as 69.6 kilometer per second per, that is Hubble constant as 69.6 kilometer per second per megaparsec. Now, using this net-right calculator, and with specific with the known redshift for the lens as well as the source, we find the angular diameter distances as well as the co-moving radial distances, which is in turn used to find the distance between source and lens using the given formulas. These guys are the co-moving radial distances. Now, once we have all this, now the only other unknown left is the theta, the radius, Einstein radius. So for that, we uploaded the download images from the archive onto the DS9 software, and here using the region feature, and of course setting the contrast right and in the logarithmic scale, adjusting the logarithmic scale, and we found the theta, the radius of the ring, and these are the actual data images of the ring, of the ring of the data used in this project. So here I have just given 2, but it is done for all 13 lenses. Now you can see the theta is given in arc seconds. So for the first one, it is 1.254 arc second using world coordinate system. In this way, we obtain theta for all the lenses, and the D's, that is the distance, relative distance between lens, and for all the lenses, and then we apply it to calculate the total mass. Now once we have this total mass, now to know about the dark matter, we need to reduce the stellar mass from the total mass. Now, how to calculate the stellar mass? For this, we use another tool, that is aperture photometry tool. Now, this is a wonderful tool to do the photometry, and applying sky algorithm A. This means that the background sky is not subtracted, because already the images that we have downloaded have the sky, background sky subtracted. Now, and using the centroid algorithm with magnitude 0 points, that is for we have to find this magnitude 0 points from the Hubble side for this particular filter, f814 filter, and for that camera. So taking that and utilizing in the photometry tool, we calculate the apparent magnitude for each lens and within the Einstein ring. Now, here we have to be very careful because uh, lots of error crops up if the photometry is not done properly. The errors involved in the apparent magnitude should be not beyond 1 or 2%, because otherwise we may not get the we may get some absurd results. So now applying the once we get this calculate this apparent magnitude from the photometry APT2. Now for each lens, now we apply to this formula to calculate the apparent the absolute magnitude. Here there are three unknowns. The DL are the luminosity distances. Again, we take the help of net Cosmo calculator, and for the specific redshift, we find this luminosity distance from there. And now for the two other factor A and K, A are the galactic. A is the correction done for galactic extinction for the specific filter and in the direction of the sky. So it varies if the direction of the sky changes. So it need to be reduced. And so this is a correction we have to calculate it from the STSC tools, their galactic extinction tool. We have calculated A values for each of the lens, and then you apply it in the formula. Now there is K correction. K correction is due to concern with types for a specific filter, and it is a reduction factor in magnitude due to effective redshift. Now this we have taken from this paper, and for each galactic type, that is for the elliptical galaxies, and applied at different redshifts and applied in this formula. And hence we calculated the absolute magnitude for each lens. This will give us the stellar mass content of the lens. So now stellar mass, to calculate the stellar mass, we need, that is converting the absolute magnitude to stellar mass, we need this formula. And here few more concepts are to be dealt with, like mass to light ratio. So this mass to light ratio value was taken from the following paper, 1.2, that is equal to 1.23, and applied, and it is specific to for a particular system used, that is elliptical, the type of galaxies used, and for the specific filter. And the stellar mass, the here MF814 is the absolute magnitude that we have calculated, and in terms of solar masses. Now with this formula, we get the stellar mass content within the Einstein ring. Now we are equipped with everything to find the dark matter. So these are the 13 selected no, I think all are not showing. So these are the lenses selected, and the dark matter percentage, that is actually dark matter percentage I calculated by subtracting the stellar mass from the dark matter and dividing by the total mass, stellar mass from the total mass divided by the total mass and taking out the percentage. I get this following percentage. It is as the graph suggests, it is well around 90%. So though there are some variations For some lenses, right, it's ranging from around 60 to 93%. So what may be the reason for this variation? Actually, mm, actually we need to deal with the uncertainties due to the angular structure of the lens potential, as well as the substructure that may pertain in the galaxy environment, lens galaxy environment in the line of sight. So once then, if we can uh, deal with this problems, then maybe we'll get better results. Besides, I have just used 13 lenses, but this is not a very good. This may not give very good statistic. We need to use large number of lenses and need to study in different filters. I hope that will help to actually find the amount of dark matter as well as the its distribution. So, um, um, so future work with darks, I hope of doing future work with large data sets and trying probing dark matter through other methods so that we can put constraint on the distribution of dark matter. And thank you. That's all for my presentation. And now, if there is question, I would like to answer.
Yeah, thank you. Very extensive, elaborate presentation. Very well done. The talk is now open for questions and comments. Please, participants, Tim, give your reactions.
Yes. So Sukhvinder, I thought that was very well done. Also, your presentation style I thought was very good too, very polished seeming. In this case, how would you interpret the range of dark matter fractions that you saw in the end there? Why do you think you got ranges that went down to what 50% or so, all the way up to 95%? Do you have
Yeah.
an idea?
I would like to answer that. See, I think it may be maybe due to errors that may happen on my end while doing the photometry, calculating the apparent magnitude. It may so happen because I have seen the variations when the error percentage of the apparent magnitude is just beyond 10%, I was getting absurd results. So this may be one of the factors, and I'm sure the unsymmetric matter distribution may play a role. And if I'm missing something, I would like you to elaborate.
Actually, I was going to suggest exactly both of those. So I'm glad that you picked up the first one there on errors. Not necessarily your fault either, but
Yeah.
the photometry is very tricky to do. It's not just that the measuring the magnitude is relatively straightforward. However, converting it into another filter and then getting the absolute magnitude of the mass, every one of those steps has uncertainties in it. And when you've done several of those, then the errors add up. And so, yes, it can have much larger errors. It turns out not every galaxy really has the same color, for example. And in the equation that you use to convert it, we are assuming the average color for these kinds of galaxies. But some of them are bluer than others, some are redder, and so on. So yes, that's probably the biggest part of it. However, I did like that you consider the possibility that there is a different distribution of matter and of dark matter in particular in these, because we are looking in the, not at the whole galaxy, but we're looking at the mass distribution within the Einstein ring. Then we're looking in the central, maybe 2/3 of the galaxy. Some of these galaxies may have a more concentrated amount of dark matter, others may have it more spread out.
Yeah.
So I think that is a possibility there. Very good.
Thank you, sir.
Any more questions from others? Any comments? Okay, if not, let's thank Sukhwinder for a very good presentation and move on to the next speaker.
Thank you, sir.
Very well done.
Yeah.
So Sukhwinder has been involved in other projects as well.
Yes, sir. And I'm looking forward to continuing with it because now this is done. Now I will be doing galaxy morphology,
Yeah.
concentrating on that. Yeah.
Yeah. So to remind you all, like I said yesterday and even today,
Yeah.
this we are not ending this project now. This is just the beginning. All this time you are learning how to learn to get data, how to analyze and make sense out of it. And
Yeah.
let's hope you all continue with it. And we move on with the next astrosprint. And we'll discuss that later. So now I call upon Ankur Chhabra.
Thank you, sir.
Yeah, good morning, sir. I hope my audio is audible.
Yeah, we can hear you. You can share your screen and.
Yes. I hope it is visible.
It's coming up. As of now, we see a black screen. It's loading. Yeah, perfect.
Okay, so good morning, everyone, and good evening, Dr. Hamilton. So the project which I'm going to talk about is gravitational lensing and dark matter, which is supervised by Dr. Hamilton and Dr. Priya Hassan. So before starting, I would like to show you this cosmic smiley, which is a result of gravitational lensing. I hope you've seen it already. So, as the title suggests, I am going to be talking about how to find dark matter using gravitational lensing, and this is the layout of it. So, first, I'm going to talk about dark matter gravitational lensing, which most of it has been already covered by Sukhwinder and Professor Hamilton as well. So, after that, I'll show you the survey or the pictures of galaxies, of the lensing galaxies which I worked upon. And after that, I'll show you the observations followed by the methods which are being used and the reasons for errors and discrepancies and future studies. So what is dark matter? So dark matter is called dark because it doesn't emit, absorb or reflect electromagnetic radiation, and consequently it is difficult to detect. So the only way we know that it exists there is because it interacts with gravity, and it becomes really difficult for the telescopes to detect it directly because they all work on the electromagnetic spectrum. So we need indirect methods to detect it. So and how do we know that the dark matter exists? So the best evidence in a way we can say is that the presence of dark matter in a galaxy results in the flat rotation curve, which is in accord with observed values. So I'll show you a small video. I hope it will be visible. Can someone please unmute and let me know if the video is working?
Yeah, it's working.
Okay, so basically we have the two galaxies here. On the left side, what theory predicts is that as we move away from the galactic center, the velocity of the stars and the content that we have, it reduces as we move away from the galactic center because the gravity effect is reducing. So we expect a graph like this. But what has been observed in many galaxies is that the curve is usually constant, and that as we move away from the center, the velocity variation is not that much of a difference. So what could account for this fallacy or reason? So it is the many theories have been proposed, and the best we come up with is that there is matter which is almost 10 times of the stellar mass which is observable, which is around and within the galaxy. And to infer the distribution of dark matter in a galaxy, gravitational lensing is used to study how its gravity bends the light of more distant background galaxies. So what is gravitational lensing? So let's say if we are, as observer on Earth, we are trying to see a very distant galaxy, which is very faint, and it is on the line of sight to us. And within within this distance or in between the observer and the source galaxy, there is a cluster of galaxy or even a single galaxy which has a dark matter halo around it. So when we receive light coming from the source galaxy, due to the direct consequence of Einstein's general relativity, the light is bent because of the gravitational impact of the cluster of galaxies or galaxies. And as a result, we see usually multiple images of the source galaxy around this lens. So this cluster usually acts as a magnifying lens, and hence the term gravitational lensing. So the distance between, let's say if this is a lens, this is observer, and this is source. So the entire distance is the angular diameter distance, which I'll talk in a few slides. So there are three types of lensings: strong, weak, and micro lensing. Strong is easily visible distortions. We see Einstein rings, Einstein crosses, arcs, etc. In weak gravitational lensings, they are much smaller distortions. And micro lensings, in micro lenses, there is no distortion as per se, but amount of the light received, it changes with time. So these are the images taken from Hubble. This is the example of strong lensing, and this is of a weak lensing. So the major difference, as already covered by Sukhwinder, between gravitational lensing and optical lensing is that a gravitational lens is no single focal point and it produces multiple images. So I worked on 8 galaxies, which was assigned by Professor Hamilton, and these are the images in 2 different filters, and these are their shortened names. So I worked on these 8 galaxies, and you can see that the gravitational lenses and the Einstein rings are quite visible in these. So the observations, the studies show that more than 90% of total mass of a galaxy is encompassed by dark matter. And the 8 galaxies which I worked on, I found the following results. So these are the results. These are the 8 galaxies. So their total mass is calculated, and all these masses are in terms of 10 raised to the power 11 solar masses. So these are the total masses and the stellar masses. So the direct matter is calculated by subtracting the stellar mass from the total mass. And these are the amount of dark matter in each galaxy, and this is by percentage. So you can see that there is quite a variation in the values. And now I'll talk about the methodology. So so there have been quite a lot surveys, and these galaxies were selected from the Sloan Lens ACS survey 1, and all these are strong lenses taken from this paper. And the data for these galaxies are taken from Mikulski Archive for Space Telescope, or the MASS database. And to calculate the total mass, first of all, we need the Einstein radius to put it in a certain formula and get the total mass. So when we get the data of these galaxies, we use this software called SA or Image DS9. And when we open each galaxy in this, in specific scales, we calculate. So this is a picture of the DS9 software in which there's a galaxy, and we are calculating the Einstein ring. So when we calculate the Einstein ring, we record the radius, which is in arc seconds, which is called the Einstein radius. And this Einstein radius is used in this formula to calculate total mass. So you can see that these are the values, and these D values are called angular diameter distance. So angular diameter distance is nothing but the ratio of galaxy's physical diameter to that of galaxy's angular diameter. And these values are usually calculated by using a software called Nedright's cosmology calculator, and where chi is the co-moving radial distance, which is nothing but a factor which factors out the expansion of the universe, giving a distance that doesn't change in time due to expansion of the space. So as Sukhwinder mentioned in a slide as well, that the distance between the source and the observer is not quite equal to the distance of source and lens plus lens and observer, because the universe is expanding. So the galaxies are being redshifted and the distance between them is not the same. So that's why we need so that's why they do not equate to the sum of these two. And hence we use this cosmology calculator in which we put the specific values of omega vacuum and omega m. And after that, we use the tool called aperture photometry tool to do the photometry analysis. And it is used to basically get the apparent magnitude, which is then converted into absolute magnitude. And then using the mass to light ratio, we convert this absolute magnitude into the stellar mass. So this is the formula which we use. And this is the formula to use. So this is the example of the APT, where we are observing a galaxy, and after doing some uh, calculations, and I'd also like to mention that we are using the F814W filter, so that it has corresponding calibration which is to be done, which is done using APT. And after that, we are setting the certain parameters to observe the apparent magnitude. Once it is done, it is converted into absolute magnitude using this formula. So DL is calculated using the Nedrite's cosmology calculator, and these values A and K are called galactic extinction factor and K correction value, respectively. So galactic extinction factor is calculated using this extinction calculator, which is on the NASA's website. So it is calculated by putting the values of RA and DEC, which are the coordinates of a specific galaxy. When you put it down and you note down the A value of the specific filter which you are using, and K values are used for from this paper. So basically, K correction value is used, and it converts the measurements of astronomical objects into their respective rest frames because of the redshifting that is been happening due to the expansion of the universe. And the extinction is the absorption and scattering of electromagnetic radiation by, let's say, dust and gas between the emitting astronomical object and the observer. And after that, when we get the absolute magnitude, the stellar mass is calculated as using this formula. So in this, you see this, this is where we put the absolute magnitude value, and then it is converted into the stellar mass in terms of solar masses. So from these two papers, and for this specific filter, we are using this mass to light ratio, which is estimated to be 1.23. And finally, the amount of dark matter is obtained by calculating the difference between total mass of a galaxy and that of the stellar mass of the same galaxy. Now, there are possible reasons because of which the errors arise, and these are the possible errors. So imprecision in measuring stellar mass using lenses luminosity and mass to light ratio, inaccuracy in estimating K correction values for respective redshifts, error due to filter conversion using I-band instead of H-band, and error in photometric evaluations. Because in most of these cases, or in most of these steps, we are using the average values. And as Professor Hamilton has already mentioned, that the colors of the galaxies are somewhat different. Some are more red, some are blue. So for that, you need specific filters. And in each step, there is a possibility of an error which arises. So in all of these steps, it adds up to quite a few error, and which can be worked upon. And what are the future prospects of this? So calculating all these parameters in different filters and different colors, this is something I would personally like to do, and when I'll be carrying with this project, and doing more of such surveys, not just from first SLAC survey, going on to 2, 3, 4, because they have a lot of surveys. So doing a lot more surveys and finding the dark matter from it. So yeah, and these are the references which the project is based on. And I'd like to thank Professor Hamilton and Professor Priya Hassan for this. And I'll be happy to take questions.
Yeah, so questions, please.
Let's see, Ankur, this is Professor Hamilton. I thought you'd gone into that in very good detail. I noticed that you had brought up the equations for the conversion there, and you said that you would like to try doing these in other filters. In fact, by using multiple filters, you can calculate the color of the galaxy, and you can get a much better idea of how to convert its magnitudes into absolute magnitudes and to get the mass more accurately. So the problem I was speaking about with the previous speaker can be improved by using those other filters there. And it does involve more work, of course, and you'd have to look up to see what the do a little bit of not spectral fitting, but a little more tight classification on the galaxies that way. But that's a very good way of doing it. Good job.
Right. Duly noted, sir. Thank you so much.
Sorry to butt in, but so Tim, I mean, since thanks, you're already with us, right, for AstroSprint. So one other thing about these presentations, it will also give us a handle on how to pitch the next level so that, you know, students can go deeper. And the ones who join late can anyway see the videos and cover up, right? So in that sense, we know then where to, you know, take it from so that we can, you know, go beyond the basics, right? So that'll be nice. Yeah. Okay. What about other questions? Does anybody else have questions, comments? Please participate. Yeah. So we'll have our next speaker. Thanks, Ankur. That was very good. And actually, Tim, Ankur actually has an astro background. He's done his master's in astronomy. So,
very good.
So that gives him a good this thing. And so now the next presentation is Mrinalini. Mrinalini also has done her master's in astro. She's been a student of Professor Hassan also, and so she finished her master's some years back. So Mrinalini.
Yeah. Hello everyone. To share my presentation now. Yeah. Hello everyone. Today I'll be presenting my work in this workshop on galaxy morphology. Hello, are you able to hear?
All's perfect. Your screen share is fine. Everything's good. No problem.
Okay. Yeah. So we are going to have a look on galaxy morphologies. So the galaxies are gravitationally bound systems of stars, gas, a lot of dark matter, and the remnants of whatever have been there in the galaxies. So this is a huge mass when compared to star clusters or other groups. So galaxies are very, very large mass, and most of the part is again covered by the dark matter, which we don't know yet. And then there are various ways of classifying galaxies, and this is the latest method of classification of galaxies. Here they have combined the Hubble's classification and then the Dirichlet's classification, which is numbered. So these numbers are nothing but the ratios of the axis. So E0, E1 means it is completely spherical. So these elliptical galaxies are also called as late type, early type galaxies, and these are late type galaxies. And this morphology not only tells about how they vary in their looks, but also in their composition and the physics going on in the galaxies as well. Oh, sorry. Basically, the galaxy structure can be can have many parts, but the basic parts are for elliptical galaxies we have core and an envelope, and for spherical galaxies there will be a bulge and arms. Other than this, they could also have a nucleus and tails, bridges, and all those things, and these allow us to understand the kinematics of the components in the galaxy, the stars, the velocity with which it is rotating, and how much stars are concentrated, and which regions they are oriented. So all this can be understood by understanding the morphology of the galaxies. And so the features of the galaxies also tells us how could the galaxies evolve through this cosmic evolution. When throughout the evolution of the universe, the galaxies also have evolved from time to time, and whatever we are observing currently is a time snap in its period of evolution. So to understand the morphology in a quantitative manner, what we are doing here is we make a model, a mathematical model of what we have observed visually. So here we are making a simulated light profiles, and using those light profiles we are making a model, and we subtract the model which we have made with the original image. The original image we have in the form of a FITS file, so it is easy to subtract in the FITS file. So after subtracting it, whatever residual we have, so we will try to fit even for the residual until we completely fit it, and the residual will be empty. So this is in principle we have to get a clear image as the residual, but sometimes we won't get a clear image. Instead, we will have some features. So the most used model is the Cersei model, because most of the other models are derivatives of Cersei models, or special case of the Cersei model. So here every point is a function of radius. So Cersei model basically describes how the radial surface brightness changes. The surface brightness changes from the center, starting from the center to the end of the galaxy. So in this model, we basically divide the entire disk of the galaxy into a number of ellipses, or close to ellipse, and then for each radius we will assume a brightness, and we make models with that. So in Cersei model, if n is the Cersei parameter, if n is equal to 1, then it describes exponential profile, and exponential profile, it could be used for the galactic disk. Yeah, if it is n is equal to 4, then it will come for Dirac law, and then it will give the brightness profile for elliptical galaxies. So in order to do this procedure, we need data. So here in this course, we have learned about how to acquire data from various resources directly from the archives itself, and independent of the wave bands. We have gone through a series of sessions to collect data for radio bands also, and for infrared also, and even for opticals. So using a MUST, the Minkowski Archive for Space Telescope, I have got a HST data for this wide field camera. And then so here, in order to fit this file, what all we need is we need the data file, and in the data file we want the data in the form of a FITS, because FITS have a facility called the header file. So in the header file we have all the information about the data, the exposure time, the RA deck values, and every detail about the instrument and the telescope. So we have all those things there, and the the benefit of using the archival data is already cleaned data. We need not do the initial processing of cleaning the data. So already the data will be cleaned, and then we have the header information. So using this, we are going to run the procedures on the data file to acquire the parameters we need. So in building a profile for the galaxies, first, we need the PSF file. The PSF file will be provided in the form of a FITS file again, and this PSF file is dependent on the telescope, the detector, and the camera, and also in the depending upon the source region. So I haven't done this PSF generation, generating the PSF using the TinyTim software. Though I have installed it, it took a lot of time to install it, so I didn't proceed with generating the PSF. So I have used the PSF file provided by Hassan sir. So using that on source extractor. So source extractor is a program which runs through a series of parametric conditions and acquire those parameter values from the FITS file, and this parametric files, whichever we require, we can put in a file which is named the name of the file .param. So it will assess the .param file, and it will extract the values for those categories which we have given over there, and then it will store it in a file named output.sex. So from there we could collect all the values for the parameter which we require to fit in the GalFit. So GalFit needs some initial parameters to start making the model. So all those parameters we get from source extractor. So the prerequisite for all those source extractor and GalFit are, we need a sigma file, and then we need a noise file. Noise file is the Poisson error for each of the pixels in the data file, and then the PSF file. Here I have used the given PSF file for coma cluster of for the HST telescope of WFC camera, and then we need a bat pixel file. So in this case, I haven't used any bat pixel file. So it is an option. If we have, we can give, and also if there is a constraint file, that also could be given, but the first three are the most needed one. And the noise file, if we have noise file, we can give. Otherwise the GalFit itself will run over this FITS file, and it will find out the Poisson error, and it will make a noise file by itself, and it will start constructing a model based on that. Yeah. The source extractor also need the PSF file. It will use the PSF at different points to extract the parameter values. And I have already told we use it in the GalFit, and these are the many parameters which you could obtain using a source extractor, but I have used only a few of these, and here there are the most important ones which I have used is x of the image, y of the image, and a, b values will be there. X and y is the orientation of the image in the pixel frame, and A and B will be in the sky plane. So these both will be connected by the theta. So these are the values which I have got, and also the magnitude values. We need the magnitude at the effective radius. So I have used the magnitude auto, and and flux, and of course the number. When it is finding an object, it will give a number to that. So we need this number. So the number of objects will be there, and then yeah, x2 told ab theta, and yeah, out of these, I don't know where we are going to use all this, but I have used only a bunch of values, and with that I have run source extractor and found out the values which I needed for galfit, and then I have this is the galfit feed me file. So here we are supposed to feed the values. So this is the input and output, and I haven't given the sigma file and the PSF file, the same file I have used for all the images, because all the images I have done with or from the coma cluster. So this will suit all those images. So I have used only this, and then I haven't done masking, but instead of doing that, I have limited the image region. So when I'm doing for the cluster, there are many images in the same fits file. So I have found so many problems in running this, because the file which I had was a drizzled one. So it is like a block, it's like a matrix. So here when I'm giving it, the galfit is not running. So when I did imcopy and extracted only the science frame, and then when I ran, then also it was not running. So then I have found out some of the values which it needs from the header file are lost when I'm extracting only the science image. So what I have done is I have used a square bracket and put one, and then it started working. So the other one is because we don't have the noise noise image, I haven't provided noise image. It will generate the noise only using the exposure time, and sorry, it will use the exposure time, and it will give the sigma value, get the sigma values from the header file. So when that is getting lost, when I'm extracting only the science image, which is not in the header file, I don't know where to put it. So I have put only the within a square bracket, I put one, and then it started running, because it was able to assess the header information from the other two images, which is not necessary for running the galfit. So after putting that, and then so instead of removing only the image which I wanted, I have given the image region here. So it was able to fit only within this region where I wanted to fit the model for. And then the convolution box should be always greater than the region which we are going to fit, because it needs some sky parameters to convolve into to run the model. So if the convolution box is smaller than the image region, then also it stopped working. So these two I had spent some time to understand, and then the play scale, it was the same for all the images which I have used, because it's all from HST, and we can find that in the header file. And here there are the three components. I have used only these three components, but for objects where I have used multiple objects within the same region where I wanted to fit, I have mentioned 2 or 3 depending upon the number of objects in that region, and I have given a Cersei profile for all those. So right now here I have one Cersei and one exponential disk, and sky is by default will be there in everything. But if we don't have an disk, so disk, in that case we can avoid using this disk. But when we are going to fit a disk to the image, then we need exponential disk. Otherwise we can use a Cersei profile for most of the objects here. I have done for image which consists of multiple images also, and for separate separate ones also. So this is one of the image. This is the image, and this is the model which Galfit have fitted. So here it is not necessarily that we will get a good fit in one go. So in that case, when we run Galfit, so it will generate a file which is called galfit.01 with the result of the iteration, how many iterations it have done, and what are the
Mrinalini, sorry to disturb, but you're running a little bit out of time, right?
Yes, ma'am. I just finished.
Yeah.
So Galfit file. So if you want to run once again over that, then instead of using the feedme file, we can use the Galfit file, Galfit 01 it have given, and then we can run again and again until we get a proper model. So when we are satisfied with the proper model, then we could subtract the model from the original image, and then we will find the residue. If we know the function which we have to use to make a model even for this, then we can include even that one in the model to find the residual to be 0. So this is the trial I have done for image with multiple objects. Yeah. So there are 2 objects here, and I have got like this. So I still have to study more on this to understand and to proceed more. So basically, after doing this, I wanted to relate. I want to obtain the luminosity of the galaxy and to relate it to the mass luminosity relation, and to find the mass of the various galaxies, and to plot the galaxies from the center of the cluster to understand the density distribution in the cluster. And so these are the things which I wanted to proceed with. Thank you.
Thanks a lot, Mrinalini. That was very nice, very good. And the good thing is that you showed them, individual files and things. So students who would like to get into this business can,
Yes,
find the stuff they need. So feedback from the supervisor. Yeah. Comments from Tim.
I was glad to see the residual images on those fits there, because you see when you start off with the simple model, it really the residual image does really show you what other structure is in there and guides you in what you need to try fitting next. I had noticed on that, it may have been about 4 galaxies from the end, don't remember right now, where you had a very narrow one. And my sound cut out a little bit then, so you may have said this, but for something like that, it could be an edge-on disk galaxy, in which case there is a special model that is used for fitting those. And I believe that Galfit does have that, in fact. So let's see, from this one, I think it is on slide 12.
Okay.
Yeah, that one there. Which model did you fit this one with?
Mrinalini, Adel? Yeah. Mrinalini, you're muted. Just unmute yourself.
Yes, ma'am. So for this one, I have used a Cersei model and exponential disk model, only one on both.
Okay.
But I
so
have
that one,
plotted this 4 times. So this is the 4th model, and this is the residual on the 4th model.
Okay, so for this one, it looks like it may be so close to being edge on that there's a special model to use, and let's see here. There is one, I think it may be called the edge disk model. But you can look up that in the GalFit manual there. I was just looking up to see what the term was that they used. But it turns out that even the exponential disk does not fit that well once you get to exactly edge on. And well, there's a special type that comes up then. But that it's interesting to see how you have that the distortion in the inner part of the disk there. And it may be that this is a warped disk. You have gravitational instabilities, one edge of the disk pulling on another, or for that matter, maybe you have a bit of the bulge, which is distorting this. Maybe it's rotating at a different angle. And you're looking at some of the dynamics there, which would not have been visible otherwise. So that's very interesting.
What about some dust structure? Could there be a inclined dust thing or something like that? Or? No.
Actually, that's true as well. That could be as true as well. It's always very hard to tell when you don't see the dust lane, whether you're getting subtle effects on the dust. You would expect there to be a little bit less dust in the center of the bulge. However, you can get it there, and if you're viewing the galaxy edge on, then you can certainly have clumps of dust there that will lie in the galaxy plane. However, the fact that this is such a almost perfectly anti-symmetrical pattern makes me think it might not be dust, but it might actually be a real warping of the disk.
Yeah, it looks a perfect warp, though actually this data is there in two wavebands. There's 814 and 475. So one can check those to see that. But yeah, it really is very beautiful, very nice, I mean, it's.
I have used only 814 for all images because they said that the chi-squared value will be close
to.
Right.
That's right.
So.
Yeah, this is I-band. So this is, Yeah, but interesting. Yeah, individual objects are interesting to check. But I was unaware about this edge-on GalFit. Is that there's a separate edge-on GalFit? This thing I was unaware of that. So thanks for letting me know that, Tim. I'll check that out and see. I didn't know about it. Yeah. Okay. Very good. So thanks, Mrinalini. Any questions, comments from the others? Any questions, comments from the others? Yeah. So let's continue with the next one. I think next is Chiranjeevi, right? Chiranjeevi, you can share your screen. I think we have Chiranjeevi, Mudassir, Avik, and Ayush. Right? Yeah. 4 more to go. Chiranjeevi, you need to unmute yourself and share the screen. Chiranjeevi, are you there? Or maybe Mudassir, you continue, and then when Chiranjeevi comes back, he can. Where is he? I don't know. Mudassir, you can continue.
Good morning, ma'am.
Yeah, unmute yourself and share your screen.
Okay. And can you see my screen?
Yes, all is good. Now go on slideshow mode. Yeah, on screen slideshow mode. Everything is fine. Yeah.
Okay. Good morning. I'll be talking about Extractor.
Mudassir, you need to go on slideshow mode. Sorry, you need to go on slideshow mode.
Sorry.
click on slideshow and no, click on here, slideshow. Yeah, or do F5. You should start slideshow before sharing. What happened? Why is it not coming? Well, they said unmute yourself. Yeah.
Okay, ma'am. Is it coming?
Yeah, but it's not on slideshow mode. It's okay. You can do this also, but you'll have to move the slides yourself then.
Okay, ma'am, I'll do that. So
But
basically, what I'm doing is we're doing iso. Yes.
Okay.
So what we are doing is we are doing isochrone fitting to find the distance. So in the first we actually took many clusters, and this cluster is a cluster 3293. I've taken the virtual observatory Tomcat, and this radius is 1 degree. So these are basically, this is the PMRA versus PMDEC plot, and this is the cut blob. Basically, what I'm doing is we're trying to filter out the members, because there may be some members which might be having the same velocity, but they're not the members. And we're doing this filter just to reduce the number of stars so that we can get a good number of members actually. So this is the plot. We are reducing the number. So this is the stat table where we can find out there is a very good change in parallax. So I can tell you the values later. And this is the second one. This is the parallax cut. So we did this parallax cut because there might be some stars which must be sitting over there. They might not be having the same might be moving in the same direction, but they cannot be members. So why we do this parallax cut is so that we can reduce that number of stars as well. So we can find only those stars which are most probably the members. So if you see here, these members 0.1 to 0.3 something, these are actually not members. So this line is basically the line for members only. So after that, what we did is, what we saw there was a gradual increase in parallax. So in the first case, in the PMRA PMDEC plot, parallax was approximately 0.342126, and the standard deviation was 0.406. When we did the parallax cut, the parallax came out to be 0.366, and the standard deviation decreased. It came out to be 0.080. After that, what we did is we plotted color magnitude diagrams. So the first one, this red one, is the color magnitude diagram of all the stars. This one is the color magnitude diagram which was plotted after the first cut, that is PMRA PMDEC cut, proper motion cut. Next is this is the green one is the CMD of the stars after the parallax cut, and this one is the subset from these stars, because if you see there are some stars which are away from the main sequence, so we try to just remove them and draw a subset over there. After that, what we did is, since we have to fit isochrone, so there must be some calculation. So from the table which you provided us, we calculated the E B minus V value for this is 0.333, and the log of age is 6.75. So since we need E BP minus RP, the formula is E B minus V into 0.77, so which we got 0.2564. Again, the AG value, which is 2.6629 into EB minus C, it was 0.8867. So when we go for isochrone fittings, we have to do these corrections so that we can fit our isochrones. So this is the isochrone fitting. This is the normal isochrone which we got. After that, I did the reddening calculations. I put the value I subtracted the value 0.2564 from BP minus RP. So this shifted a bit. This is our cluster and this is the isochrone. Now we have to fit it. So what we have to do is, we have to take into consideration the extinction factor, that is AG. So after that, what we got this. So if you see here, this is, since isochrones are usually done by using the absolute magnitudes. So if you see here, it is G max plus 12.7. So 12.7 is basically the distance modulus, including the AG factor. Since we know the formula, which is written in the next slide, it is like this. So M minus M, that is the apparent magnitude minus absolute magnitude, that is which is known as distance modulus. This is 12.7. So we know the formula is M minus M is equal to minus 5 plus 5 log of D plus AG. So we can say 12.7 is equal to minus 5 plus 5 log D plus AG. So AG we have calculated, we'll put those values and we'll get log of Distance is 3.3628. So from this we can find the distance. Distance will be 10 to the power this, so it will be 2305 parsecs. We can also find the error, which is approximately 252 parsecs. So we can find the distance using the isochronous fitting as 2305 plus minus 252 parsecs. And if we check the table, the distance which was written there, that is 2441 parsecs. So we are quite close. So this was about 3293. I have done the same thing for many other clusters like 581, 2224. In 581, it also came same, but I have one problem. It was in 6893, NGC 6893, where when I used this extinction factor, the distance reduced to a very large extent. I got it around 900 parsecs, but it is actually it was actually 1764 parsecs. So I don't know why it is. So if you can please tell me. So this is for 581. Also, the distance after doing the isochronous fitting was 1674 plus minus 376 parsecs. From the table, it was 2199 parsecs. So it was almost very close. Next is 2244. For 2244, I got 1706 plus minus 135 parsecs. And from the table, it was 1532 parsecs. For 2264, I got 605 plus minus 25 parsecs, and from the table it was 650 parsecs. And for 6231, I got 977 plus minus 77 parsecs, and from the table it was 1393 parsecs. So I think to almost all the clusters except 6893, this isochronous fitting gave us a very close value of the distance. But in case of 6893, 6823, sorry, the distance I got from isochronous fitting was something 700 or 800, but the actual value is 1764. I don't know, maybe there is some problem with the AG value or not. But rest with all these values, all these clusters, I got the value which was almost close to the one which was given in the table. Thank you.
Thanks, Mudassir. That was a good presentation. But you can already envisage what are the extensions. Like when we started the Gaia projects, that's what I showed everybody, that initially you can do it with TopCat, right? But then the step ahead would be to then start using it with Python, right? And then there are specialized codes which are used for isochrone fitting, so that like now when you're fitting it visually, right? But you could actually do it through a code so that for each point, one minimizes the dispersion and gets it in that sense, right? So there are many ways to extend this work, which I hope you'll be doing. So
maybe we can do the next sprint.
Yeah. So by then you can get on to doing that business. Instead, that's for all the people who are doing the Gaia one, that you are doing it with TopCat for simplicity, but that's just to teach you the method. But then later on, you should move it to the code, which will make it much more specialized, right? And it'll have its own benefits, right? So thanks a lot.
Yes,
and do we have any questions?
Thank you, ma'am. Thank you so much.
All right, thanks. Yeah, and Adi, do we have any questions from anyone? Good, very good. And finally, you should make a table with all the values for everything, because that's what I want all of you all to compare, because you're all doing the same sample, huh? You have a table.
Yes, ma'am, I have the table.
Yeah. So please, everyone who's presented today, please send me the PDFs. I don't need your PPTs. I want the PDFs of your presentations, and preferably a document. No, what is this? No, not this. This is the stats. I'm telling you a table which compares, I think I gave you a sample of 9 clusters, right? So for all the clusters, the values you got.
Okay, ma'am, I'll send you that table.
Yeah. So please, everybody send the reports and all that also, because then I'll put that up on the website so that whoever would like to access our material, right, they can see your videos and they can access the material. I've even requested people to give me the Python notebooks if they've used that, so that, you know, see, the biggest advantage of us doing it on the net in this kind of a way is that people to whom all this is inaccessible, they can access it through the net. they can find your notebooks, they can run it, and they can actually get into this work, from a distance, even if they are not this thing, right? That's the biggest advantage of online, that it's accessible to all those who have a net connection. So there would be a whole bunch of students and people who would be interested in seeing this analysis, right? So please add your reports, add your Python notebooks, add explanations, so that a student who wants to get into this business can get into it, will at least know from where to start, right? Otherwise, most people don't know what to do, right? So yeah, thanks a lot. So now,
Thank you.
we'll go to the next one, who's
Hello, ma'am.
Chiranjeev. Chiranjeev says
Yes,
he
ma'am.
has a net problem. Let's hope he can manage now.
Yes, ma'am. My voice is coming.
Yeah, very good. We can
So,
hear you.
ma'am, actually, the net is unstable from last 3 hours. I don't know. So, if it
No
breaks
problem.
between
We'll
my
try.
presentation, please allow me to start.
No problem. If there's a problem, I'll WhatsApp you or whatever. Okay, don't worry.
Yes, ma'am.
Yeah, continue.
I'm sharing my screen. Hello. My screen is visible, ma'am.
Not yet, but it says that you're going to share. It says Chiranjeev has started screen sharing, so it will just give it a minute. Yeah, this is your desk. Very good. It's come. Now put it on slideshow mode.
Yes.
Press. Yeah, perfect. Very good.
Yes, ma'am. So, yeah, hello and good morning. I'm myself Chiranjeev Kunda. I've done this star cluster analysis with Gaia EDR3 under the supervision of PS and ma'am. So, yeah, star clusters, as we know, stars are never born in alone or in isolations. They're born in groups from the same molecular cloud. These stellar groups are basically called the clusters. And as all the cluster members are formed from the same molecular cloud, they have the same chemical composition and the same age and same approximately lie at the same distance. So, but they only differs by their mass. And as you know, there are basically two types of star clusters. One is open cluster and globular clusters. So I have worked on basically on 4 open star clusters, namely NGC 581 and or the Meteor 103 and the NGC 6913 and NGC 1960 or the Meteor 36 and the IC 1805. These are the 4 clusters I have worked on. So I taken the data of Gaia EDR3. Gaia is basically a space observatory by European Space Agency, which is measuring the positions or distance and motions of stars with really at a high precision with accuracy of 2 microseconds. And its catalog releases in stages, and EDR3 is the recently released one on December 2020, and I've used that EDR3 data, and I have used the TopCat as a tool to analyze the star clusters, which is basically a graphical viewer and editor for tabular data and developed by Mark Taylor. So yeah, I have used the for analysis, I have used the the same procedures I have followed to analyze to get the distance of 4 different clusters. So first I plotted the data and visually selected the probable cluster region, and then I check and apply the cuts to eliminate the non-cluster members. Then I make the color magnitude diagram with the data, and then applied the photometric cut to eliminate the remaining non-cluster members. Then fit the data with appropriate isochron, and finally calculate with the final values the distance and the transverse velocity as well. So yeah, I'm starting with this NGC 581. So yeah, first I just have plotted. Yeah, from here I'll explain all the steps for each of them, and starting with this one. And so yeah, first I have calculated the data by taking the 1 degree cone radius, and then plotted as a scatter plot with proper motion array and proper motion deck in x and y axis. Then I visually selected the region uh, which might be the desired cluster, or the cluster we want to see. So here it is. Like the region I've selected in the blue one. Um, then I plotted I then I visually selected after selecting the region. I make the sky vector where we can see all the stars are moving in random directions. But if we look at the selected region, all these stars are moving almost in the same direction. So from which we can conclude that they are at least most of them are the cluster members. So as I know, the stars of the same cluster will lie in approximately at same distance. So I found the mean parallax from the selector region, from the statistical data of the statistics of the selector region, and from that mean parallax I have calculated the mean distance, and I made a distance cut with the stars lying near this mean. So which is approximately at the same distance. So most of the stars are lying at the same distance. So after that, I went for creating the color magnitude diagram, um, and this is the color magnitude diagram with the distance cut. So here you can see there are few contaminations are there, which are, so I made a photometric cut on this data, and this is my final data. Which I am going to fit with the isochrone. Uh, so at first I found the log age of this constellation, that ISO 7. So 7 point, yeah, I found the log age is 7.3. So I downloaded the ISO 7.3 file and tried to fit the data with this isochrone, and uh, then I also found the distance modulus and the reddening, the EV minus V from the MWSC catalog. So then I subtracted these values from X and Y axis, and adjusted it by doing few plus and minus, doing few adjustments. The cluster data fits the till the cluster data fits the isochrone, and finally I take these values, this adjustment. After the adjustment I take these final values to find the distance, and I have calculated with that, and I found, finally I found the distance is 2061 parsecs, and for reference, for the comparison, I have taken this distance from the NWSC catalog, where it is 2199 parsecs, so which is a bit close. So we can, so just for comparison I have taken this data. So after that also went for calculation of transverse velocity. So as I get the mean proper motion PMRA and PMDEC values here, I calculated the mu, or the proper motion thing. So from that, with that, for the transverse velocity, so this formula I calculated this 0.21 mu by d, proper motion by distance. Like I found the transverse velocity to 0.154 kilometer per second. So this is all for NGC 581. Then I did almost the same things for NGC 1960. I selected the scatter plot, and then selected the region near it, which might be the data, which might be the cluster, and these blue dots are that selected region, and this is the statistics for that selected region, where we can see the parallax is 0.80, and from that parallax value I have calculated the distance thing, and by taking that mean distance I have taken the nearby stars. The same things I have done here. Then I have done the photometric cut on the distance cut, and finally get this nice data. So which I got with the fit with the isochron file. So here I tried to fit it, and with the using the distance modulus and the reddening value. So here you can see it is almost fit with the first attempt, and then with just a little bit of tweaking, we fitted over the isochron datum. So these are the final values I got, and then I went for the calculation of the actual distance to it, which I found 1027 parsec. And for comparison, the distance to end with the NWSC catalog, we found 1200 parsec, which is, yeah, it's not bad, yeah, near about. So then I went for the proper motion, using the proper motion thing. I have calculated the transverse velocity, and I found the 0.703 kilometer per second for NGC1 and 60. Then I went for again for NGC 581, and actually these are the sorry. Okay. NGC 581, this is the sky vector for the selected region, where you can see almost all the stars are moving in same direction. And then I did the same photometric cut and the distance cut. And yeah, so I don't know, it is not showing number of slides. Okay, so hello, am I audible?
Yes, yes. I'm sorry. I think mine was unmuted, right? I think I get disturbance. I'm sorry.
No, it's fine.
Continue.
Yes. So yeah, now let's start for IC 1805. Here I don't so this is actually for yep. So this is for IC 1805, where when I tried to fit it with the isochron file for that, which is 6.8, I found its log is, and then I fitted it. So, and after final tweaking, I found this reddening and distance modulus final values. Then I take that and calculated the distance to the IC 1805. So, and I found the 1799 parsecs, and the distance from MWSC catalog, I found 1700 parsecs, so which is very close. So, and then I with the mean PMRA and PMDEC data, I found the proper motion, and eventually I calculated the transverse velocity, which I found 0.114 kilometer per second. So then I went for NGC 6913. Then with the same data, I started with a scatter plot, and I selected the blob, which I thought is the probably cluster member. So then I made the distance cut, the same thing I've done, and then went for the fitting the photometric cut, the final data with the isochron file, and this is what I got when I tried with the initial values for distance modulus and reddening. Then this is after the final taking, which is not very accurately fit, but still it is the best what I could do here. So then I found these values. Using those values, I calculated the distance, and in this case, I found 1002 parsecs, and for comparison from the MWC catalog, where the distance is 1173 parsecs, which is again near about. Then using the mean proper motion and the proper motion deck, proper motion area and proper motion deck data, I calculated the proper motion, and then calculated the transverse velocity using the same formula, which I found 1.408 kilometer per second. So yeah, these are the all the things that I have done yet. Thank you.
Thanks, Chiranjeevi. I'm sorry that there was a point where I think mine was unmuted and I think there was some disturbance. But that was a good presentation. Um, uh, just for improvements, like I said, the whole thing has to be moved on to Python code, number one.
Yes.
Number two, according to me, your conversion for transverse velocities and all is not correct because you have to multiply your new RA into a cosine delta function. You have not done that, right? Because it has
Okay,
to,
ma'am.
so the transverse velocities, according to me, which you have are not right. They need to be corrected. But we'll work on that. I'll send you that material about it. And so that you'll need some corrections. And very good, well done. And we hope now in Astrosprint, we will take off from here. Okay. So assuming that people know what are isochrones, how to fit them, what to do, then we can take this to a higher level, right? To another level. So that's very good. I'm just happy that all of you all have understood this concept well enough. That's why you did it for a whole bunch of clusters so that, you know, you get an idea of what has to be done. And we'll take it forward in Astrosprint. Yeah. Thanks a lot.
Yes, ma'am.
Thank you.
Thank you, ma'am.
Thanks.
Ma'am,
So now the next one is we have Avik, right? Avik, it's your turn, I think.
I have a question.
After Avik, we have Ayush. Suman, are you presenting? Suman? Suman Pramanik, are you presenting?
No, ma'am. I have not ready my presentation.
Okay, so I mean, just to be nice to you guys, in case you need a week or two more to present, yeah, we can still do it. So in case you can finish the work in a week or two, you can contact me and we can have the thing, right? So you're most, because you were there at the morphology sessions and all you were attending, right? I remember he was attending. Yeah. So in case you need some time to finish your thing, no problem, we'll give you time. Yeah, you can do it later. Avik, you can start sharing your thing. You all have permissions.
Yes, thank you, ma'am.
I had a question for Chiranjeevi.
Oh, sorry. Yeah. Okay. Go ahead. Mudassir, go ahead.
Yes, sorry. I just want you to go to that slide where you calculated that AG factor. Because I think you're using is.
Avik, you'll need to unshare because he's referring to one of Chiranjeevi's slides. So please unshare and Chiranjeevi, just share your slide. The one that he's asking about. Yeah.
Sorry.
Which slide, which cluster are you talking about, Mudassir?
First cluster where you are calculating the distance. The AG
no,
value.
but which one?
AG value, I just want.
Which one?
The first cluster, I think it's the fifth slide.
Okay, so that is 581.
Calculated the distance modulus.
Okay, I think that is 581.
Distance modulus.
First one was 581. Okay.
581.
Okay.
I think Chiranjeevi has. I think there should be a problem from his side. He has
he
left.
was saying he has some net issues. He's disappeared. Yeah.
Yeah.
Okay, fine. Then Avik, you continue. When he comes in, we'll. Yeah.
Surely, ma'am.
Okay, ma'am.
Surely.
When he comes back, we'll ask him.
Sure.
He has some net issues. Chalo, Avik, you can go ahead.
Yeah, thank you, ma'am. Okay. Good afternoon, one and all. So my task was to see whether NGC 2452, which is a planetary nebula, is a member of NGC 2453 using Gaia EDR3 data. And let's see. Okay. So am I audible and my screen is being seen?
Yes, everything is perfect. Your slideshow is perfect. Your voice is good.
Thank you, ma'am. So the content is as follows. So first I go ahead with the analysis of NGC 2453. I have divided it into two parts, mainly estimating the parallax distance and distance modulus. And then the second part is reddening, extinction, and corrected distance. Also, I have analyzed parts of NGC 2452, which is a planetary nebula. I have taken only the central star in the planetary nebula and gone ahead. So next, I go ahead with the conclusions and the work ahead, which I would like to do. References, acknowledgement, and open for discussion. Okay. So said that, this is the area. If we see from ESA sky, this is the cluster. This is actually, if we type NGC 2453, this is around this area, the star cluster, and this is NGC 2452, which is planetary nebula. This is seen using the all-wise, so we are seeing actually a huge region compared to what we see in the optical bands. So it is still debated why this planetary nebula is actually a part of this cluster or whether it is not. So we start with analyzing the cluster and finding its distance and extinction. So the idea is to get Gaia EDR3 using TopCat virtual observatory tools, mainly the cone search, and go ahead with open clusters in proper motion plots and selecting a portion and finding the mean parallax, standard deviations, and all these things. Then finding out the distance, deviations, and errors, and the distance modulus. This is the part one. So I start with showing the area. So this is how it is seen in Gaia ESA sky. So all these sky plots are actually detected by Gaia EDR3 data. And now I turn to TopCat cone search using the VO tools. And I take a 9 arc minute cone radius. This is as suggested by Gonzalez et al. 2019, which suggests 8.5 arc minute to 10 arc minute radius. So I have taken a median value of 9 arc minute. And this has resulted me 6,527 results out of the Gaia EDR3. Next, I obviously plotted along the PMRA and PM deck to get a blob of stars. But if we zoom in, we get a small blob, which is actually the cluster. Obviously, we can see that this is ahead of the proper motion, not the 0, 0 value. So it should not be a background star cluster, right? These are not background stars. These are proper cluster stars, which has a proper motion in both Ra and deck. Going ahead to plot the parallax of the subset NGC2453, it's a neat subset, but there are errors. So getting to parallax cuts, which will actually clean up the mess. So I have my first parallax cut was around from 0.01 minus 0.01667 to 0.51667. This was the first parallax cut. I did a Gaussian fitting of the parallax cut, which was done, and I got a standard mean of around 0.236 and a standard deviation of 0.09. Obviously, this is very high standard deviation. And so I go on doing the parallax cuts, useful parallax cuts, I would say. And this is the superimposition of all the parallax cuts of I did. And you can clearly see the Gaussian fits are beautifully fitting, and the standard deviation is going less and less of the mean parallax. So this is where I end up in NGC 2453. I have named here PCUT 6. To cross-check these stars, I plot them using a sky vector plot, and I see almost all the stars are aligning themselves in the same direction. So that cross-checking is also done. Next, what I did is since the Gaia limit is around in G band is around 21 magnitude, there was huge crowding in the lower portion of the stars. So I put a threshold limit of 18 magnitude so that the crowding is removed in the lower parts, so that any false detection can be removed. And the rest of the things after I cut it off. So this is again I have renamed this as NGC 2453 PCAT 6 MCAT 18, which you can see as blue dots here, and the red dots are beyond the threshold of 18 magnitude. You can see this superimposition of this plot. The standard deviation has now reduced to only 0.016, and we will also calculate, which is only a 7.86% standard deviation of the mean parallax. This is less than 10%. Going ahead, these are the statistics of the subset, which I have just pointed out the main statistics. So here we can see, and we will calculate it later, the percentage errors. So parallax and parallax errors, which are standard deviation is much less. PMRA, the standard deviation is again much less. PM Tech, the standard deviation is again much less. Going ahead, I have used Jupyter Notebook to do the calculations. Of all these distance modulus and everything. So first putting in the values what we get from mean parallax and standard deviation, we have got a distance of 4734.1311 plus minus 372 parsecs. I will actually here, due to calculation, I have used the maximum decimal digits, but when we report it with rounded off figures. For calculation, I have used this. Again, the distance modulus is coming around 13.37, and we will use this in the further calculations, mainly in the reddening and extinction. I should note again the 7.86% error of the distance and the parallax, and the proper emissions is around 2.56% error and 1.9% error bars. Next step is to find the reddening, extinction, and the corrected distance. So I plot the color magnitude diagram of open cluster 2453 with the isochrones of 40 million year and 50 million year. These two 40 million year and 50 million year are suggested by again Gonzalez et al. 2019, and this after plotting, after superimposing these two, we can clearly see that there is extinction because of the interstellar dust. So I need to correct for the extinctions and things. So from the Milky Way star cluster catalog, I obtained an interstellar reddening value of 0.666, and applying that extinction in G band for Gaia using the formula of 2.629 and factor, we get it 1.774 magnitude. Implementing the all this to correct for the shifts in the color magnitude diagram compared to the isochrones. So I put the distance modulus and extinction correction in the y-axis, and only the reddening correction in the x-axis, as the x-axis is only the magnitude, right? So we can see there is even with the data given in the Milky Way star cluster catalog, we still see a shift. It is not in proper fitting, at least visually seen, when we seen visually. So I go ahead with doing with the trial and error values of reddening EB minus B, and I take instead of 0.166 on taking 1.25 magnitude of reddening. I see that this fitting is much better compared to the 0.666 value. Going ahead, this is case number 2. Going ahead, we can still see, if this is the color magnitude diagram, there is a small bump which is almost equivalent to this and this bump. So I try to fit this bump in between these two, which makes this fit much nicer. But I had to add I had to subtract 0.5 from the distance modulus of 13.3. and visually this fit is much nicer and proper compared to the other previous fits of the isochrone and the color magnitude diagram. So again, uh, in line with Gonzalez et al., we conclude that that age must be around 40 to 50 million years. But here there are some interesting things I would like to point out. One is the fit with the 1.25 reddening value and my subtraction of zero point 0.5. The fit is much nicer. The second thing is these three individual stars, these one which needs further investigation. One might be, this might be a giant, these two may be pre-main sequence stars, which are very interesting compared to the whole HR. And no matter how many times I have done the fitting and everything, these three are very prominent and very proper um, stars. So this may be a good, interesting point to go ahead. Okay. So I have taken for the calculation these three cases, mainly one with 0.666 and one with 1.25 EB minus B, and one with 1.25 and a subtraction of zero point 0.5. So I start with 0.666, the as given in the Milky Way star cluster catalog, and on seeing this, we get our corrected distance around 2000 parsecs, uh, which is of the order of what is given in the Milky Way star cluster catalog. But going ahead, uh, we see that with the 1.25 EB minus B, we get a much lesser distance, around 1022 parsecs, 1 kiloparsecs. And if we subtract from the distance modulus, then also it reduces much to 811 parsecs. So this, I would later conclude that this, the uh, if the fitting is very proper and errors are much lesser, then we can conclude that there is a huge amount of dust which is in between us and the cluster. So these are the summary of the calculations of the distance, which is direct distance. This is 4.7 parsecs around and plus minus 0.37 parsecs. And the three cases where we find the corrected distance to be 2000, 1000, and 800 parsecs, respectively. Okay, going ahead with the analysis of NGC 2452. Here I should mention that NGC 2452 was first discovered by John Herschel in 1847, and it was one of the first planetary nebulas to be detected. And he, on his both the observation, this is very interesting to read, on both the observation he couldn't understand what it is, so he saw it like a fuzzy object. And we still see this from the ESA sky, and this is from the Hubble Space Telescope data. So what I have did here is to club all the three filters of Hubble Space data, and did a stacking and give a bit of rotation to see that which is the main central system compared to all the other stars which are maybe in front or lying around. So I assume that this is, and we will see why. So uh, going back to ESA sky, if I put a magnitude threshold of 18 magnitude, and from other sources I have seen this to be lesser than 18 magnitude. This must be the central star. All these ESA sky, Gaia EDR3 actually detects all these clumps as one stars, but these are false positives. So this must be the central star. So I have taken the central star. I've just taken the parallax of the central star, central object, sorry, star, not star, central object, parallax and the errors, and calculated what the distances could be and the distance modulus could be. So there is no extinction correction, and these are to be done in future. But at a first approximation, calculation, what we can see is it's around 2.941 parsecs plus minus 692, which is comparatively less than what we saw in case of NGC 2453, which is the open cluster. Um, this is what Gonzalez et al. Says is around 3.7 kiloparsecs, which is after applying the dust maps. But this has not applied all these calibrations, dust extinctions, and everything in this calculation. So to go ahead. Uh, so again, I would like to appreciate this point that in the near the star cluster, you can see a huge amount of dust. This is the cluster. This is the planetary nebula, and so I thought of just seeing whether this is in other region, other observations also. So what I did is I did a log plot of the star cluster and the planetary nebula, and you can see the clear dust, uh, huge amount of dust, because log plot actually makes out the dust, the fainter sources much higher. So you can it is more clear in this this spectra, this plot, this image actually. Okay, so I'd like to conclude my analysis of NGC 2453, which is an open cluster, and NGC 2452, which is the planetary nebula. So NGC 2453, the mean parallax, the distance calculated from the mean parallax is around 4.7 kpc plus minus zero point 0.3 kpc. And this is in agreement with Gonzalez et al. Although here we are considering almost 81 stars compared to 11 stars considered in Gonzalez, and much lesser in other previous works. The error percentage that I have seen, it's only 7.86%. Proper motion, we have not calculated the proper motion fully, but I have just calculated the error bars of proper motion in RA and proper motion in TEC, which are much lesser. Um, Next is the fitting, which we did for the three cases. The extinction values and the corresponding distances, I have tabulated it here so that it is easier to visualize the whole thing. So compared to 4.7 kiloparsecs, what we get here is 2.1, around 2.1 kiloparsecs. If we go with the extinction value, reddening value as given in the Milky Way star cluster catalog. But if we do trial and error with 1.25, we get much lesser corrected distance. And if we do with the 1.25 and a reduction in the distance modulus, then we get around 811 parsecs. So probably we need more further investigations in the bus. We can say that there is much amount of dust which is present between us and the cluster. Um, Analysis of NGC 2452 gives us the distance to be 2.9 parsecs plus minus 0.372 parsecs. But the distance error, obviously, because I have used only one point to calculate the central object distance, so the distance error is much higher. So comparing this and this at the point, first approximation, we can say that we can suggest that the planetary nebula NGC 2452 is comparatively nearer to us compared to the NGC 2453, which is the open cluster. Obviously, it should be subjected to further in-depth analysis in beyond. So the work ahead, which I would like to do, probably the part of Astro Sprint, is having better values of extinction of NGC 2453 by calibrating each and every individual of these 81 stars. Then extinction of the planetary nebula is a very different aspect in itself. So I would like to adhere to that, address that. Compare with the previous result of Gonzalez et al., which they did using the DR2 data, and obviously investigating the three interesting stars, the main sequence and maybe the red giant. Maybe we need further investigation to conclude this. These are the references which mainly the Gonzalez et al. Paper, the Gaia collaboration, uh, the Topcat paper, and other isochrons and everything. Um, uh, Acknowledgement part, I would first likely to acknowledge Dr. Priya and Dr. Nazam. Thank you for this whole workshop. You taught us a lot. Various resource persons today, Dr. Tim Hamilton was also present. So thank you for your time, your effort to teach us without apart from the curriculum. I would like to acknowledge the Gaia collaboration for making their data public so that we can do this whole project. The ESA Sky, the Top Cat, obviously the virtual observatories. I've used a bit for the from the ARSA archive and Mikulski archive also, so I would like to acknowledge that. And last but not least, I would like to acknowledge out, Office for Astronomy and Development of the IAU for providing this opportunity of learning to everyone. Thank you. I open the floor for discussions. Thank you.
Thanks, Avik. That was a good presentation. Very nice one. And yeah, what excites me is that all of you all have future plans, which is what is necessary. Like you see that, like see your case in this, you went into details into a single cluster, right? So when you go into single clusters, also there are so many other aspects which require attention. First of all, about those three stars, I didn't know about them earlier. But first of all, you need to check whether the errors in their proper motions, etc., and their distances, how large are those? Are we sure that they are members or no? Number one. I mean, so this is for you to do, and this is important work because this can actually lead to a decent publication because it would be new, unless somebody else has reported it, which I'm sure they haven't. The other important thing for you to do is to plot those three stars, right, on the array deck. So see where are they located. Are they lying in a dusty region closer to the Planetary Nebula, or where are they actually sitting, right?
Okay, ma'am.
And when you see where they are sitting, what is important then is to overplot on that infrared data, okay? Because infrared data tells you where is dust. So
Yes,
plot near infrared, mid infrared, far infrared, radio, all these things will give you dust. So dust and gas. So what you need to do is see where they are, overplot on that region, all
Yes,
this
sir.
infrared data so that you know where is the dust sitting. Okay, why? Because their position could be like that because of dust, right? So they've basically got moved from there, the position they should be. They've got redder. They've moved to the righter part instead of being in the left part, right? So instead of being on the main sequence, they've moved towards the right because there's lots of dust. So the dust could either lie on the star itself, or it could be that the star is located in some region where there's lots of dust. So that you'll be able to see if you actually see it in infrared as well as in radio, right?
Surely, ma'am.
Other
Okay.
thing you can and should do
Hmm.
is for those three stars, there are different methods with which you can cross match it to other catalogs. Okay,
Okay.
cross match it to catalogs ranging from ultraviolet to infrared. Okay, and you will plot what is called a SED, spectral energy distribution, right, for each of those stars. So
Yes,
you
ma'am.
will, it's like you'll get like a black body function, right? But you will have the points. So you'll have the points for all these different filters, right?
Yes.
Ultraviolet, optical, infrared, whatever, all those things. So you'll have their individual SEDs, right?
Yes, ma'am.
And from the SED, you can very well see if there is dust playing the role, because what does dust basically do is that it will absorb the emission and re-emit. right?
Yes,
So
ma'am.
if there is dust playing the role, then suddenly you will see, I mean, I can't show you, but you can Google and see the spectrum or the SED of a dusty thing. So a dusty thing will be, like that, and suddenly at the infrared particle.
It will increase.
Yeah, so that will show you on your SED. So see, the game that you're playing is, even if you say, so first thing you got to confirm that they are members, right? Second thing, if they are, then check their locations. And if dust has got to play a role, right, you have to validate your proposition that it's dust by putting in, like I said, the infrared maps or whatever, as well as the SCDs. Huh? So with the SCDs and all, you know what kind of a structure there is. You can also look whether these stars, is there some spectroscopic data, depending on how bright or faint they are. They are reasonably bright. They're not too faint. So you may even have some more data about them and check about those things. And if all those things don't fit, then the other question is that what are they doing over there, right? So other options, see, you always need to remember in a cluster, you could have a star at the same distance, which is not a member. You can have a star which is moving with the other stars, but is not a member. But these stars seem to satisfy both those criteria and still not be members. So then we need to, so in short, it's a detective story which you need to build up. But at every stage, you have to have concrete evidence to validate, right?
Yes, obviously.
Ah,
Obviously.
yeah, but the binary may not. You can have a binary or a variable. A binary generally gets pushed up, but generally by 0.5 magnitude. So in certain clusters, you'll see a binary main sequence and you'll see the normal main sequence. But this is a bit too much. This is a bit too much. You can't go that far.
So these
So
three are completely in
yeah, so
different.
check on this and get back to me on mail and whatever, and we can check on this. Right?
Surely.
Okay. And I'm sure it has not been reported because, like I said, there is a beauty and interest in understanding structures in the sense of a large sample, say 9 clusters. And there's also importance in studying an individual object also, because an individual object also can have something special about it.
Yes.
Right? So we can just check. See, these can even be that even the Planetary Nebula is in the foreground, this thing is behind. So maybe there's some dynamics in which these guys got thrown over there, something like that. You need to know where they're sitting in the cluster, in RA deck.
Yes. I had one question which I would like to discuss. Is since we have plotted the open cluster at around 40 million years to 50 million years, now these are very young stars, and planetary nebula, if there is, so we are expecting it to be a low mass star and also at a very high age, right? So can we conclude from that also that it is not a part of the system?
Correct. But then you should have a way of, can you age the Planetary Nebula? I'm not too sure.
No, I have not done that, but
just check on that.
Ma'am, how can I do that?
I don't know. I'll have to check it myself because you are right that a planetary nebula is not from a very massive star. If it's a not very massive star, then it lives much longer.
Yes,
it lives more than 40 million years. And if it is longer than 40 million years, it's not part of this thing.
Yes.
Right? So that's also an argument. But like I said, in the scientific process, you have arguments, but you have to have what do you say? Very concrete and logical flow of thought to justify your argument. So your line of thought is right. It's good. But then you should also give me an estimate of the age of this, etc., and something like that. You understand what I mean?
Yes,
that we have to have concrete things to validate our argument.
Yes, ma'am.
Yeah, you have to fight your case. Whatever's your case, you have to fight it with concrete evidence. Not because you think it is like that.
Yes, obviously.
Yours and my thoughts don't make a difference. It's what it is. Yeah. So like what Sir is saying is that since there's a nebula, though the nebula is not associated to the cluster, but since it's in the foreground, it can play a major role in reddening.
Yeah.
Because it's in the foreground, it's in the front, no?
So I would show this thing. That's why I checked it with
With ESA sky, you'll be able to very easily point where is it located in the cluster.
so this is the sort of 1 second. Oh, I am not sharing. I'm not sharing. Fine. So this is the cluster, and this is the planetary nebula. And what I did is I went to Ursa to
Yeah,
see the
that's where
dust
you should
lens.
go.
So this is the planetary nebula here, and this is the central star. So this is the central star. This is the central star.
And where are these three guys?
Oh, that I have not seen. That I have not seen.
You need to see where they're sitting. And that you get to know from infrared.
That I will check out from Ursa itself.
Yeah.
But these dust lanes, I would like to point out, these are huge amount of dust which
Exactly.
are here. So
Yeah.
can it be only due to the planetary nebula, or it can be else?
That you
Because
should tell me.
okay, 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 ma'am. I would.
So actually what people do is, ideally, if you had spectroscopy for every star, then you would know. Now
Yeah.
you don't have spectroscopy. So what you do is you build an SED. How do you build an SED? By cross-matching across catalogs, and you have points. So photometry in principle is broadband spectroscopy, right? So you will have the points on your thing and you build the SED, that kind of a thing. So actually, let's stop over here, but there's lots you can do with this thing. So you go ahead and you mail me, and we'll be in touch, right?
Surely, ma'am. Surely.
Yeah.
Thank you.
So now we have the last one. Or Tejinder Pal, are you also ready?
हेलो
Yeah. Hello, sir. Are you
नो
ready?
मैम नहीं मैम मैंने चेंज करवा ली थी ना डेट आपसे 7th की
हाँ ठीक है तो आपका 7th का कर लेंगे ठीक है
yes
no problem ठीक है
thank you
चलिए so
thank you
now we have Ayush is the final one
Good
just
afternoon.
before lunch come on
Yeah. Good afternoon, ma'am.
hopefully when we have our what do you say offline sessions even we can feed you lunch but chalo Ayush
Ma'am, is my voice audible? Hello.
we can hear your voice we can see your screen now go on slideshow mode
Yes, ma'am.
yeah from current perfect everything is good
Yeah.
chalo.
So today I'm going to present my study of open clusters on NDC 1960, NDC 581, and NDC 3293. So we'll start with an introduction. What are star clusters? Star clusters are a group of stars that have a common origin, and they're bound together because in a cluster, all of them will be of same age. So there are different two types of clusters we know: a globular cluster and open star clusters. Globular clusters are located on the halo of the galaxy, while the open star clusters we see them on the disk part of the galaxy. But since both of them are star clusters, they do share same properties like normal star clusters possess, like in the color of the stars indicate their age, and they're together. I mean, they are at the same distance from the Earth as we measure. So we are using HR diagram to estimate what is the age of a star cluster where it is, the distance. So HR diagram gives us the, here the HR diagram shows the main sequence, which shows this thing, the color depicts the temperature of the star cluster. So how, the left part, the blue region is means the star is it's very hot, and when we shift to the right, the temperature decreases. So this graph shows us the evolution of a star, how it goes through. So same, but to plot the same thing, we use a color magnitude diagram, which is a form of HR diagram. In color magnitude diagram, we plot the apparent magnitude versus the color index. So apparent magnitude is the magnitude which we know of the star cluster. So we use the isochrones to find the age of the star clusters. So here I've shown four age isochrones. Like the red one is a 10 billion years, then the yellow one is 1 billion years, and the this green one is 100 million years and the blue one is 10 million years. So this isochrone depicts that all the star, iso means same, I mean, and chrone here is constant age. So on a isochrone, supposedly on a blue one, all the stars of the same age exist, but there are different points due to their mass. So my objective was to extract the data from Gaia using TopCat software, and to find out the distance modulus, distance extinction reddening of the star clusters using TopCat and Python. I mean Jupyter Notebook. So what are the steps I have followed? First, I've extracted the Gaia data using TopCat software, doing a VO cone search. For all the clusters, I've used a 1 degree radius. Then using a proper motion analysis, I've done a plot of PMRA PMDEX scatter plot to find the cluster member. Then I've determined the distance. I mean, I estimate the distance of the star cluster using the parallax, which I get to get a rough estimation of the distance. Then I plot the HR diagram. By plotting it on, yeah, plotting a plane plot to and I plot. I mean, I make different subsets, so I eliminate the field stars. Then I fit the isochrones. Fit the my star cluster to different age isochrones to find the age, because this is the way we find the age of the star cluster. Then using the values of distance modulus and reddening, we find the corrected distance of the star cluster, and the same I've done with Python. So these are the calculations, and some formulas which I've used. Like to estimate the distance, I've used the formula. Distance is 1000 by parallax. Reddening, I've used a conversion factor because we're using Gaia bands, and extinction for the same I've used conversion factor. We use reddening tells us about the x shift, and distance modulus will give us the y shift. That is the difference. I mean, what is uh, I mean, why the isochrone and the star cluster are different positions? That gives us the proper estimation of the distance using the distance modulus. And extinction, we subtract the extinction because of presence of dust in our line of sight. And I've selected these three clusters: NGC 1960, NGC 581, and NGC 3293. So my first one is NGC 1960. So as I said, I collected the data using a VO cone search of 1 degree radius, and I did a PMRA PM deck plot, a scatter plot to find the cluster member. Then I've done a parallax histogram to find the estimation of a distance. So here our peak shows that the distance of the star cluster is somewhere here. Then I've made different subsets and created, eliminated the field stars, and the yellow one over here shows my star cluster, and the red one is the whole data which I collected from Gaia EDR3. Then I've tried to fit the star cluster to the isochrone. Here the log age of the isochrone is 7.5, and my distance came, or the corrected distance came is 1032 PC. Same thing I followed for NDC 581, and I've plotted a parallax cut, and I have created subsets and found the star cluster. Then I have tried to fit it to the isochrone. Here the age distance of the star cluster is 2046.077 PC, and log gauge is around 7.3. And same thing I've done from NTC 3293 using the parallax cut and estimated the distance. Then I have found the cluster members by eliminating the field stars, and here I plot it over the isochrone. So my log age of the star cluster is 7.1 and distance is 2035.89 parsecs. So the conclusion over here is I found the age and distance of the star cluster using the color magnitude diagram and the data from the Gaia EDR3. Oh, okay. And the analysis and calculations of the star clusters were done using the necessary formulas and the parameters calculated like extinction value and reddening value. I even calculated the uh, velocity. So positive velocity indicates that star clusters are moving away, which even signifies that a universe is expanding. And the parallax method gives us an estimation of how far our star cluster is, and the ages we estimated using the isochrones. I would like to show the Jupyter notebooks here. So this is for NGC 1960. I collected the data using TopCat, the same data I've used over here. So I have this over here. I have used three isochrones of age 7.4, 7.5, and 7.6 log age. Then this is my data of the star cluster. The one is full data and one is the but after eliminating the field stars. I have plotted the data. So here the red one shows this is my cluster after eliminating the field stars, and the yellow one is the full data. After that, I've tried to plot it over the isochrone. So my log age isochrone is 7.5, and then I've estimated the distance using the distance modulus, reddening value, extinction value, and then I found the distance over here. Same thing I've done for NGC 581. This is my star cluster. Then I've tried to plot it over here on isochronous 7.3 log age. And same thing I've done it for the last one. Oh, yeah. Yeah, this is for NGC 3293. This is the isochrones. I've used three isochrones. First to try which one it fits. It was fitting. So this is my first cluster data, and it was fitting best on 7.1. So I've used this isochrone. So it gives us an estimation that the age of star cluster is around 7.1 log age. Mm. So this was it, and I've used a reference like Gaia site is reference. I've used a paper, Astronomy of Open Star Clusters by Pawan Tiwari. Then I've used some two sites, one Cosmos and Buro and buro.cwr.edu for reference. And this is all. And I like thank Priya ma'am and Hassan sir for conducting such a wonderful workshop. Thanks, ma'am.
Thanks, Ayush. Very good. And congratulations. You are the one who actually did the Python notebook, which I've been telling others also to do.
Thank you,
Because
ma'am.
so that's really good. And see, I mean, we've been teaching for many years. So often what happens is all students are capable of writing their Python notebooks, right? But
Yeah.
the first step is what is a little intimidating or scary. So that's why, for example, when you share your notebooks, that's what I'm telling everybody to
Yes,
share.
ma'am.
So then what happens is the other person who's not yet started doing that, he can see yours and he can say, okay, see, this is how he's done it, right?
Yes.
So, I mean, we've also been students ourselves. So once you've
Yeah.
seen that somebody's done it in a particular way, right?
Yes.
Then you can do it, you can adapt it, you can improve it, you can, build on it. But when you've never seen it, then people are like confused. What's a notebook? How do I do a notebook? What do I write?
Yes.
So I do hope that this initiates everybody into the coding process, because that is very essential for data analysis, right?
The advantage is these notebooks is once it is you
Yeah.
Yeah. And then another important objective of us wanting you to do coding is that, see, it's obviously I'd like everybody to become an astronomer. All of you all should become astronomers. But the thing is that if by chance somebody has a change in their career also, for whatever reasons, you may go into something else. But these are skills which will help you in whatever you take up in future, you know. So for example, even if you don't do analysis with astronomy data, you do something else, you get into something else, right? It could be a whole range of career options. But once you know you can code and you can do something, right, you can always use that for whatever else you want. So it also serves the purpose of, you know, skill building, right? The objects you use your code is for is it varies, but if you have the skills to do that, right, then a person who's employing you will always know, okay, I can take this guy and, you know, he's done coding for something. So if I want him to do coding for sales in my shop also, he can write code for that, right? Yeah. So I don't want you all to do that. Sorry, I don't want you all to do that. I have no such plan. But the big picture is that you'll all have to be employable. You have to be open to different kinds of, you know, areas and work, and developing skills of these kind can be applied to many more things, right? Yeah. That's an important factor, right? We understand. Okay, so we'd like to thank all of you all very much. This has been a very interesting journey with all the talks and all the sessions we had and everything. It's been nice to have all of you all. And we are obviously planning to meet you all more. So I'm going to, I'll send you all mails. But if you want, I can actually show you in advance. The problem is the homework I had to do, I could not finish doing it for various reasons. But one sec, I'll just, yeah, okay. Yeah, it's come here. So I just want to show you all in advance what you all will be getting a mail for is that, yeah, I'll just do it. So you're going to see the new workshop, which the new thing that we're going to do. This is called, it's here. I hope you all can see it. This is our new thing, which is called Astro Sprint. It's Star Trek themed. I hope all of you all are Star Trek fans. If you all have not seen Star Trek, please see it. It's good fun. So in short, Astro Sprint is basically, I can't get back here. Yeah, so basically it is, if you read on here, we're basically going to have 3 workshops. There will be one workshop which we have in, yeah, so that's the website. So you will see that we basically have a series of 3 workshops. Sorry, this has to be corrected. One, so these are Star Trek themes. So the first one is Enterprise, which will be 26th to 28th of March. Okay, this will be an online workshop because we can't travel. But I do hope that the next 2 in the series, this is Discovery, which will be in July. And the next one is Next Generation. This will be in November. I'm sorry, this has to be corrected to November. And this will not be in March. So March will be online, but we hope that July and November will be offline and we'll all personally meet each other. And we'll be having these 3 workshops. In the meanwhile, I will send you all mails about this. But what you'll see is that, okay, it's not yet put up over here, but this website, you have the workshops, you'll get it too. You can go in from here also. We will start registrations for the workshop. I'm just going to have to do some little bit on the website. So that's for Enterprise, and there's Discovery, and there's Next Generation. So you'll have to register for this. This will be all on Zoom because I don't think we can travel. This is too soon. And so when you enter in here, we are still developing the website. So that's why there's, you know, not everything is there. So when you register, we have an online form, and you'll be actually doing this for registrations, right? The website will also have a blog and a forum. So in the forum, the social media now will get transferred. Instead of doing it on Telegram, we'll have it on the forum itself. so that in the forum we can have different channels on different areas, and people can discuss things. So the idea is, in the first workshop we seed your thoughts and your plans for projects. So when you discuss in the forum with us, with the mentors, we will then get you all ready for the July session, right? So July, hopefully when we meet, what we plan to do is it'll be a 50-50 thing. Half the presentations will be by y'all, by students in July, okay, on their projects and their presentations. And half of them will be new material with which you can further build on for the November session, right? So November, again, we'll do 50-50. Students present 50%, we present 50%, yeah? And in advance, I can tell you that from the OAD, we've got some funding, and the funding is basically going to be used to give you all some amount of travel support, as well as support for the conferences, right? So for the workshops, we plan hopefully not to charge you all much, as well as minimize those costs and give you all registration waivers as well as travel waivers, right? That's what we plan. So I'll soon send you a mail about the thing. There's a little bit of work to be done still in the website. That's why I'm not doing it just now. But
Ma'am, sorry to disturb, but have you decided?
So the home button is the Earth. We have a nice student who's actually made the website. Yeah, what were you asking?
Ma'am, I was asking that have you decided on the topics that are going to be covered in this workshop?
Yes. So even that, I'll put it up on the website. So we'll continue with the Galaxy Gaia thing, right? That'll anyway be on. We'll have some separate sessions on statistics by Tarun Deepsaini from IIC Bangalore. Then we'll be having Tim Hamilton will continue with some new topics. We'll have Patrick Das Gupta from DU doing cosmology. We'll have a separate session on Chandra X-ray telescope by Jonathan McDonald. We'll have Sushant will be continuing with us. All our old people are there with us. So Sushant will be there with us, and Professor Deshpande will also be there with us. So,
ma'am, can we have a session or like a small workshop on N-body simulation as well?
Sure, we are planning an N-body simulation thing also. But this is 3 days, so it's packed in 3 days. So, yeah, so yeah, so maximum what we'll be able to squeeze is 1 or 2 sessions in this, right? And then if there is more, we'll have separate, what do you say, satellite workshops, which will be on specific topics. Like Professor Deshpande wants to do one on Monte Carlo simulations. So we may have a separate one on Monte Carlo. We may do a separate one on N-body, but we'll have to plan that after the March thing, right? So March, I'll also in the registration form, good idea. I'll even add another question on, topics which you all would like to be covered, right? So we can check up on that.
Ma'am, would we be doing like this itself, like more than 2 also we could do?
Yeah. You can do how many ever you want. And as it was there in this case, everything will be recorded, everything will be online, so you can cover up whenever you want, right? So no problem. That's for March.
Okay.
Then July, November will be hopefully offline. Then we'll have to see how to record it and video shoot. Okay. So we'll keep in touch and we'll send you a mail very soon about all these other things. But keep looking out for Astro Sprint, right?
Ma'am, what's the March date?
It's a weekend, 26, 27, 28, the last weekend of March.
Okay, 26.
Friday, Saturday, Sunday, because we, in terms of our timetable and all, Saturday, Sunday we don't have class, and Friday is a good day to attach, right?
Okay. I am in science education, so my Saturday, Sunday generally doesn't.
Our problem is we have a job, right?
Yeah, obviously.
And we have to teach Monday to Friday. But
ma'am, I am associated with Vikram S. Sarabhai Community Science Center.
Okay, so where are you? Where exactly are you located?
Ahmedabad, Vikram S. Sarabhai Community Science Center.
Okay, 1 minute. Let me just stop this live stream. And thank you very much. Thanks everybody for being with us.
Before we close, happy National Science Day.
Happy. Same to you, sir. Same to you, ma'am.
The
Yeah.
credit
National
It's
Fest.
a happy
you
Thanksgiving.
wanted, we could continue it. Yeah, since you all were consistently attending and participating, that adds to the success of all this. So the major credit goes to you,
Yeah.
not us.
Thank you. You give us a reason to work. Chalo.